In the last two videos I've looked at our current car situation, and the result was that one should really go and be very largely replaced by more cycling combined with public transport. And that would save perhaps 3/4 of the CO2 emissions from our current use. Presently that's about 2,500 miles a year, and that would save about 300 kilos of CO2e annually. The main car could be usefully replaced by an electric car, and after a few years the net carbon footprint of the manufacturer would be offset by the travel emissions. These would be greatly reduced, perhaps by about 1 tonne or so per year. But what might the other effects on the environment be? What will be the effect of getting the resources to fabricate the vehicle? The main effects are the key elements on the battery and in the motor, and these can be set against the need to use some of the precious metals in exhaust cleaning for internal combustion engines. These catalysts can contain, among other elements, platinum, palladium, cerium, and for petrol engines also rhodium. There are a few grams of these elements in the catalyst in a car exhaust system, and because they are so precious, extraction processes are very well developed, and so recycling is viable. The very strong magnets used in the motors are based on rare earth elements, also known as lanthanides. The mass of the magnets in electric cars is about 2 to 5 kilograms, and that's about 1,000 times greater than the PGM catalysts in petrol cars. One class of magnets is an alloy of samarium and cobalt, and another, rather stronger, is based on neodymium, iron and boron. That's mostly iron. There's about 28% neodymium. So there is about 300 to 1,400 grams in a motor of an EV. Any battery system must be a rechargeable one. And the two most used are nickel metal hydride, that's NiMH, and the lithium ion. Both provide much higher energy density than a lead acid battery, so less weight is added to the car by the battery, and both battery systems are widely used. The nickel metal hydride form the bulk of the rechargeable ones that we might buy, but many fixed systems use lithium ion: cars, computers, cameras and phones. In each case, the names of the battery indicate only part of the story. Taking the nickel metal hydride first, the cathode is a nickel hydroxide and the anode is the metal hydride. The charge is conducted in the battery electrolyte by the movement of solvated protons, that's hydrogen ions. The metal is typically an alloy of nickel and a mixture of rare earth elements with cerium, lanthanum, neodymium and praseodymium. That's a mixture which comes from the rare earth extraction. Actually, in terms of weight, the major component of the battery is the steel case, about 44% with nickel and nickel hydroxide, about 24 to 30%, and the lanthanides about 7%. There may be about 2 kilograms of rare earth elements in a battery for a hybrid EV, more than is in the motor magnet. In a lithium-ion battery, the lithium-ion Li+ conducts the charge between the cathode, which is based on metal oxides, and the anode based on graphite. Again, the case is a significant component in terms of mass, about 40% with the cathode, 10 to 27%, the anode 10 to 18%, and the electrolyte 10 to 16%. About 2 to 8% of the battery is lithium. In an EV, a typical battery might contain 6 to 10 kilos of lithium, with a hybrid having just about 10% of that. Based on these figures, the cathode material of an EV battery may have a mass of about 60 to 100 kilos, and of that, a third of it is oxide and 2/3 the metal. And the archetypal element for the cathode oxide is cobalt. So 40 to 60 kilos of the battery is cobalt. These elements are not the most common, so before we jump towards an EV as a way to reduce emissions in the atmosphere, which is much needed, what are the consequences of using these metals? This table is taken from the British Geological Survey and was published in 2015. The rare earth elements are at the top of the risk chain, and shown in red. Cobalt is in the orange risk category, although its source in the Democratic Republic of Congo presents some pretty significant issues. The precious or platinum group metals, palladium, rhodium and platinum itself, are thought to be of less risk, as is lithium and natural graphite. The very abundant element carbon makes this up. Now this graph shows a more recent risk register for elements key to high technologies. Most of the red elements are rare earths, and two can be seen as being so in coming years. Both are key to high-performance magnets. The supply of lithium is expected to be under more pressure, shown here as moving up in importance and also in supply risk because of the lithium-ion batteries. So this gives us some pause for thought about our car. And in the next couple of videos, post-holiday that is, I'll look into the developments in magnets and batteries aiming to provide sustainable futures as well as lowering atmospheric emissions.